Here's a short mini lesson going over the ideas of one-dimensional elastic collisions. Okay, and the elastic collisions oftentimes give students a little bit of trouble, and as well as experienced teachers. Remember, elastic collisions are totally bouncy, and the kinetic energy after the elastic collision for the objects, the sum of the kinetic energy is equal to the total kinetic energy before the collision. So kinetic energy as well as momentum is conserved. So I can write the two equations down. One would be the law of conservation of momentum. Okay, so that's what the momentum before the collision. It should be mass 1 times v1 plus mass 2 times v2. Remember, momentum is mass times velocity. That momentum before collision is equal to total momentum after collision, m1 times u1. I'm using u to describe the velocity after collision, plus m2 times u2. Okay, some people use little prime marks or subscripts for the velocity after collision, and I just use the letter u. So this would be conservation of momentum. I'll just abbreviate it here. Okay, and the second equation that is very helpful for elastic collisions is the law of conservation of kinetic energy, and that only applies to elastic collisions. So remember, kinetic energy is 1/2 mv squared, so I'll apply to this term, and I'll apply to this term, and then these right here. So 1/2 m1 u1 squared plus this 1/2. And so this would be the conservation of kinetic energy, and I just abbreviated. Okay, now having two equations, that will allow us to solve for two unknowns. For example, if we were given the two masses and the two starting velocities, we could find the final velocity of each mass. We could find u1 and u2, but it would involve some algebra, and that's what makes it difficult. So there's a nifty way to make the job easier, and that's to use these and develop a little theorem, a little relative velocity elastic collision theorem that will help us circumvent some of that troubling algebra. Okay, so I'll just show you how to derive that. First, I'll rewrite equation number 1. So I'll rewrite equation number 1 in terms of differences in momentum. So that top one, if I pull m1 u1 over to the left hand side and pull m2 v2 over to the right hand side, we will get this. Okay, so you can see this is just a change in momentum of mass 1, and this over here is the change in momentum of mass 2. So we can call this equation 3, I guess, something like that. Equation 3. It's just a rewrite of equation 1. Let's rewrite equation 2. So we'll do a rewrite of equation 2 in the same manner. So I'll just pull all the m1 terms over the left and all the m2 terms over to the right, and that'll give us the equation in terms of difference. So this would be 1 times the quantity v1 squared minus u1 squared equals, now the mass 2 m2 terms would be on the right, u2 squared minus v2 squared. I'll call that, well, before we call it anything, let's expand that out using our idea of the square of the differences. Remember, like, look at this one here. This would be like a squared minus b squared. remember a squared minus b squared is equal to a minus b times a plus b. So we're going to use that concept of the differences of squares, expand these out, and that will be helpful. So I'll move this up a little bit. And so now we're going to take this one here, and this will be then m1 times v1 minus u1 times v1 plus u1. So the quantity m1, and then we're using the difference of the squares there. Let's do the same thing for this side. So this would be m2 times, now let's use the difference of the square, u2 minus v2 times u2 plus v2. Okay, so now that gives us a valuable equation here, so we can call this number 4. Okay, so we rewrote the conservation momentum equation into this form here, and we rewrote the conservation of kinetic energy equation into this form here. Now let me move this up a little bit here, and now if we divide equation 4 by equation 3, okay, our mass terms will divide out. So basically, let me show dividing it with a different color. So I'll take equation 4 and divide it by equation 3. So it'd be m1 times v1 minus u1 here, and then on this side that'd be m2 times u2 minus v2, right? We see that the m1s cancel out. m2 divides by m2. We get v1 minus u1 dividing out over here. We get u2 minus v2 dividing out here. And so what we're left with then is v1 plus u1 on the left hand side, and that's equal to u2 plus v2. Okay, and so that's no matter what the masses are, it's irrespective of mass. Okay, so this is what happens when we divide equation 4 by equation 3. We get that. Now it's a little, so that would work for you. That's a nice little theorem there. But usually the way people write it, they just tend to put all the v's on the left and the u's on the right. So getting v's on the left, we'll just take this v2 here, subtract from both sides, and we'll take the u1 and subtract it from both sides, and we'll get v1 minus v2, okay, equals u2 minus u1. And this, my friends, is a very useful theorem. We can call it maybe something, let's make up a name for it, relative velocity elastic collision theorem. Okay, and so here's our final result. And basically what this tells us is this difference here, v1 minus v2, that's the relative velocity before of the two objects before the collision, and this is the relative velocity of the two objects after the collision. The relative velocity of the two objects before collisions equals the relative velocity of the two objects after the collision, no matter what the masses are. Okay, But this only works for elastic collisions and only ones that are one-dimensional. In other words, they're not glancing. So it only works for one-dimensional, in other words, non-glancing, like in other words, direct hit, right? Non-glancing elastic collisions or interactions. So it only works for one-dimensional, non-glancing elastic collisions. Let's see an example of this, huh? Okay. Let's take an example. Let's say that we have a 3 kilogram mass, 3 kilograms, and it's going to the right at a velocity v1 of 10 meters per second. I'll just put plus 10. We'll define to the right as positive. And it's going to collide with another ball elastically. So these are like billiard balls, but they're not the same size. This only has a mass of 1 kilogram. And it's going slower. It's going at a speed of plus 4 meters per second. Notice this one, they're both going in the same direction. Or other problems could be going where you have the objects moving in opposite directions. So this one's going at a plus 4 meters per second. This one's going at a plus 10 meters per second. And you can see that this one's going to overtake this one and collide with it. So this is the before collision situation. Remember, this is going to be elastic, and it's one-dimensional. I'll just put 1D here for one-dimensional elastic collision. Before the collision, it's this situation. So what we want to find, this is what's given. Find the velocities after collision. In other words, that would be like u1 and u2. So we want to find the velocities after collision. In other words, we want to find u1 and u2. Okay, so how do we do it? Well, let's use our little handy-dandy relative velocity elastic collision theorem, which says, remember the theorem, our useful theorem, maybe that would be a way to write it. Our useful theorem says that the relative velocities of the relative velocities of the masses before they collide, so that'd be v1 minus v2, are equal to the relative velocities of the masses after they collide, and that would be u2 minus u1. Notice how the terms are, the 1 and 2's are switched. The relative velocities before, it's v1 minus v2. The relative velocities after would be the u2 minus u1. So they're switched, which is what we had originally in the derivation. Okay, so we're going to apply that useful theorem. We're also going to apply the law of conservation of momentum with it too. Okay, so this useful theorem has both the law of conservation of momentum built into it and also the law of conservation of kinetic energy built into it. And it doesn't matter what the masses are here. So that's really nice. So let's go ahead now and substitute in what V1 was. Well, V1 was 10. Okay. And then we can minus what V2 was. V2 was a plus 4. So we have 10 minus 4, and that's equal to U2 minus U1, which we do not know. Okay, well, just simplifying it, 10 minus 4 is 6. 6 equals U2 minus U1. Okay, good. Now let's use the law of conservation of momentum. Conservation of momentum. And that basically says what? m1 times v1 plus m2 times v2 equals m1 times u1 plus m2 times u2. We can go ahead then and substitute our values into it. Okay, so m1 is 10. n1 is 3 kilograms times the velocity of 10 plus 10, and now plus m2, which would be 1 kilogram, times the velocity of 4. Okay, and that'd be 30 plus 4, or 34 there. That's equal to m1, which is 3 kilograms again, times u1 plus m2, which is 1 kilogram, times u2. So 34 equals 3 times u1 plus 1 times u2. Okay. Well, since we found this right here from our little useful theorem, we can find let's say u1 in terms of u2. Let's do that. So u1 would be equal to, if we're just rearranging this, that'd be equal to u2 minus 6. And now we can substitute that right in here for u1. Substitute that in for u1. So we'll get 34, let me move this up again, equals 3 times the quantity u2 minus 6, because we've substituted this in for u1, okay, plus 1 times u2, or just u2. Okay, now just doing the math here, let's just simplify it. We get 30, I'll just expand this out, 34 equals 3u2 minus 3 times a negative, or minus 3 times 6 is minus 18, plus u2. Okay, so we'll add 18 to both sides. We get 34 plus 18, that's 52. That's equal to 3u2 plus u2. Okay. And let's see what else we get here. So that now we end up with 4u2 on this side. Oops, I better put the 2 there. So we get 52 equals 4u2. So therefore, u2 would be equal to 52 divided by 4. And I'll get the handy calculator out. 52 divided by 4, that gives us 13. So 13 meters per second. So that little ball is going to pick up some speed, isn't it? It's going to be going 13 meters per second instead of the original 4. Now if we take that value for u2 and substitute it back into our original little theorem equation, right back here, substitute that back in, 13 for u2, we'll get 6 equals 13 minus u1. Oops, I better move that up. So I just substituted 13 back into our useful theorem, substituted 13 right there, and so we'll end up with what? u1 equals 13 minus 6, or in other words, 7 meters per second. Okay, so in other words then, we have u2 equals 13 meters per second, and u1 equals 7 meters per second. That would be the final answer. Let's check and see if that makes sense. Okay, so these are before collision. After collision, this one's going to go from 4 meters per second to 13 meters per second. And this one's going to go from 10 meters per second down to meters per second. Kind of makes sense, right? Okay, well, thanks a lot, guys. Bye.